Hello? Today I briefly discuss and compare both Keplerian and Newtonian physics for describing satellite orbits. I use the term Keplerian physics when referring to the laws of planetary motion formulated by Johannes Kepler. These provided the foundation for celestial mechanics and laid the foundation for Newton's law of universal gravitation. I use the term Newtonian physics to refer to Newton's work, which provided a theoretical basis for Kepler's observations of celestial mechanics. Based on Keplerian physics, the distance from the center of Earth to a satellite is given by the equation I now show. In this equation, r is the radial distance to the satellite from Earth's body's center, a is the semi-major axis for the elliptical orbit, e is the orbit's eccentricity, and theta is the true anomaly. I show the elliptical orbit in the next image where the semi-major axis is defined. When the eccentricity of an orbit is equal to 0, the orbit is circular, and the semi-major axis is the same as the radius of the orbit. According to Kepler's laws, this is a perfect two-body system where Earth is perfectly spherical and is the only source of gravity. Also, the satellite's gravity does not affect Earth's orbit. To describe this orbit, Keplerian orbital elements are used. These are semi-major axis, eccentricity, inclination, longitude of ascending node, argument of periapsis, and true anomaly. For a perfect system described by Kepler, these are all static except for true anomaly, which defines the location of the satellite in orbit. However, there is no perfect two-body system because other source of gravity do exists. When using Keplerian physics to model satellite orbits, other acceleration sources are accounted for by using mathematical perturbation theory. The result is that the orbital elements are not static but change with time, and orbit models based on Keplerian physics with perturbations are not accurate for long missions or missions that are relatively far from Earth. However, they are very fast when calculated using a computer, and is the reason for their continued use when many low Earth satellite orbits must be modeled simultaneously. Newton developed a theoretical foundation for this orbit, and it is described by the second-order differential equation that I now show. In this equation, Gm is the universal gravitation constant multiplied by Earth's mass. The arrow over radius indicates that it is a vector, and the double dot over radius indicates that it's the satellite's acceleration. When this equation is solved numerically, it produces the perfect Keplerian orbit. To account for other acceleration forces, we simply treat them as other inputs, like I show in the next equation. When solved by computer using numerical integration methods, this results in a satellite orbit model that is accurate over long time periods, and if all sources of gravity from the Moon, Sun, and other planets are included, it can be used to predict spacecraft motion throughout our solar system. Although this Newtonian physics model is accurate, it is relatively slow compared to the Keplerian perturbation model. On the other hand, computers are getting very fast, and a multi-day lunar orbit simulation can be accomplished in as little as 3 seconds using a standard personal laptop. For more information about modeling satellite orbits using Newtonian physics, see my book on the subject. Thank you for watching this video. Don't forget to like the video if you found it informative or useful.